Hello, everybody. Come on in. Anybody have any questions? Only got three of you in here so far. I'm sure it'll be coming.
Professor, I think you forgot to update the day for the online test number 2. It says that it expired yesterday.
Okay. Actually, I thought I corrected that already. Let's see. Online test number 2. Thanks for letting me know that. I'll pull that up real quick. Yes. It should be, I think, September 25th, but I got to see whether that is appropriate. Online tests. Yes. I must have, I don't know how I did that, but anyways, I'm fixing it to the 25th. That gives you until Monday. Actually, I might, let's see, you guys meet on Tuesdays and Thursdays. So yes, it'll be the 25th at 11:59 p.m. All right. So yeah, that should be working now. Thanks for letting me know that. Would have definitely missed it otherwise. So. Was that Tony or Randall who let me know that?
Yes, Tony.
Tony, okay. All right. Well, it is 2 minutes after, so I really should get started. We've got some material to cover, that sort of thing. When we last spoke, I had actually worked out the idea of an electric field as opposed to having to just use the force equation. So there's actually ultimately 3 versions of Coulomb's law. We haven't covered the third yet. But the first version was that F equals K Q1 Q2 over R squared, or F equals Q1 Q2 over 4 pi epsilon naught R squared. That again is a version of Coulomb's law. It's the actual magnitude of the vector force that acts between Q1 and Q2. So I told you don't use negative signs in there for your charges, just treat them all as positive. And then it has a corresponding set of sentences or descriptions that go with the equation saying that the actual direction of the force is either repulsive or attractive, depending on if the two signs are, or if the two charges have the same sign, then it's repulsive. If they have opposite signs, then it's attractive. But in both cases, it acts along the line connecting the two particles Q1 and Q2, or if they're not particles, you might luck out and they'd be a spherical distribution of charges Q1 and Q2. If that's the case, then you just use the center of the sphere as if it is a particle. But if it's not spherically distributed charge, then you actually have to go through a whole nother process, which we don't have to do at all, but you'd have to think sort of where's the center of charge, sort of like the center of mass that we found in 241. So that's the key thing, is to understand that that formula gives you a magnitude. You have to work out an actual vector direction that acts along the line connecting the two centers of charge of the two charges. I then introduced the idea of the electric field by taking and considering, instead of F equals Q1 Q2 over 4 pi epsilon naught R squared, I used F equals Q, like a big Q, times little q over 4 pi epsilon naught R squared. And I imagined that the portion of the force that came from little q was the multiplication of little q. So if I divided out that force by little q, I would get a thing called the electric field, whose units were newtons per coulomb, because it's basically the same thing as Coulomb's law of force, which gives you newtons, but I've divided out one of the charges, so that's newtons per Coulomb. But again, you have sentences to make that into a structure. One sentence says that the electric field points in the direction that a positive test charge would be compelled to move, or the direction that the force would act on a positive test charge. So now what you have to do is imagine a line that connects the charge big Q, the one that we're treating as the source of the electric field. If that's a point charge, then it's just from that point. If it's a spherical distribution of charge, then it's just the sphere, the center of the sphere. If not, again, we have to do that whole center of charge stuff. But again, we're not going to have to do that in this course. So you take a line that connects the charge big Q to the point in space that you wish to know the electric field. That's where you're going to pretend the test charge will be. And that line connecting that point in space in Q is the line along which the electric field vector acts. So for instance, if big Q is positive, then it's going to act along that line pointing away from big Q, because if you put a charge little q that was positive in that point, it's going to be repelled by the Q. So it's going to want to go away from Q. Okay. So we got that. Now I want to give you a vector form of the electric field equation, and I want to give it to you in terms of a differential charge dq, and that's d big Q as opposed to just plain Q. Okay, so let me start by sharing my screen. Does everybody know what I'm talking about, this electric field? Do y'all recall what we did at the end of last section? Obviously, if not, you can go back and watch the video from last time, but you can also download the notes from Google Docs. Okay, I just want to make sure nobody had any lasting questions or anything like that. So now I'm in the process of trying to share my screen with you. And I've already made the drawing up, so that'll save us a little bit of time. Hopefully it will come up in a second. It takes a little bit of time. Looks like it's still working, so it should come up pretty soon. Okay, so what I've drawn here is that interpretation that I had. So what we have is the electric field. I'm going to go ahead and write that down. We had the force was equal to Q times Q over 4 pi epsilon naught r squared, where r is the distance between the center of charge of big Q and the center of charge of little q. And again, we imagined the portion of this force that was a result of little q was this little factor, little q. So our idea was to represent this with an electric field, which, for reasons that I explained before, we're going to take the limit as little q approaches 0 of f, that formula that I have there, and I'm going to write it out in its full form right now. So that's q little q over 4 pi epsilon naught r squared divided by little q. Now, the reason we're doing that limiting process is basically, if you're going to make the argument that Q, big Q, makes an electric field, then clearly little q must make an electric field as well. But what you're trying to do is imagine the scenario of the little field being, or the little charge having such a small effect that it has essentially no effect. So that's why you're trying to consider letting Q go to 0. But in the end, the formula really is just Q over 4 pi epsilon naught r squared. And that also gives us that F. If you, once you have the electric field and you want to know the force on a charge little q, that force will just be little q times the electric field, and that's a vector equation. So it automatically gives you a vector. To make the E or the F above a vector, you have to remember those sentences that I told you about, which was that the vector is either, the force is either repulsive or retractive. I just mixed the first syllable of both words together. That's called spoonerism. The force is either repulsive or attractive in F or E cases. But mainly the deal is the line that the vector acts along connects Q to the little q in the force, or in the electric field, it connects Q to a point in space where you're going to imagine putting a test charge little q. Okay. So that's what we're using right now is these versions right here. And then I just wanted to reiterate that, hey, once you use that E right there that I boxed off and calculate the electric field for that point charge or charge distribution Q, then you can immediately get the force back by multiplying it by little q. So I got to match a form of that electric field there, but I want it in vector form. So what I've drawn is a three-dimensional space. You can see your three coordinate axes, X, Y, and Z, drawn in black. I've taken the time to sort of locate a little charge dq that's blue, and you can see that has coordinates x1, y1, z1. And I just gave you that for some concreteness because I wanted you to understand that one of the ways you can ultimately calculate a vector if you so need is to literally just take the final point of the vector, which in the case of dq vector, the vector that points to dq is called r sub dq. That final point would be x1, y1, z1, and then you subtract from it 0, 0, 0, which is the origin. That's the tail of where the vector is. And then you take that mathematics that you did, x1 minus 0, and you make that now the x component of r dq. And you take y1 minus 0, and you make that the y component of dq, and you take z1 minus 0 and make that the z component. And a short way of writing that without I hats, j hats, and k hats is just using the less than symbol and the greater than symbol as opposed to parentheses. So it looks just like a point, but it uses those sharp pointy things. Similarly, RP, that's the vector R that locates the point P in space at which you wish to know the electric field, but it also happens to be at which you wish to place the test charge, the test charge that you're going to use to dictate direction and that sort of thing. So again, that vector would just be the final point minus the initial point, which would be like x2 minus 0 would be the x component, y2 minus 0 would be the y component, and z2 minus 0 would be the z component. So that's how you find those two vectors, and they're very important. So once you make a coordinate system, you're going to have to figure out a vector from the origin to the differential charge element that you're going to use, dq, and you have to figure out a vector that points from the origin to the point at which you wish to know the magnetic field. And I'm trying to draw a script P for the point, and it just looks horrible, but I think y'all get the point. That's good enough. Okay. So the sentences that I was talking about before tell us that the electric field should act along the line that connects dq to P. So the line we're thinking of here, I'm going to draw it with little red dashes, say. The line we're thinking of should be right along there. Okay, so I have a vector r sub dq. It's a little messy in there, so I wanted to zoom in and show you that that green set of letters r sub dq is the vector we're talking about. And actually, I could actually write it up here. Let me do that real quick. But that set of, or that particular vector, oh man, that particular vector is r sub dq, and it points, like I said, from the origin to the differential charge element that we're starting off with. Now, what I've found in my own experience is that differential charge element should be chosen to be like along the positive x-axis or along the positive y-axis or along that basically those two are good, or at least in the first quadrant. That's sort of the key. So when I do that, I find that I don't usually make sign errors. Whereas if I jump into the second coordinate or something like that, my x component might have a negative inappropriately, or my y component might have a negative inappropriately or something. So anyways, that's what we're trying to do. So can anybody think, you see those two vectors, rdq and rp, can anybody think of a vector operation that you can do with either one of those vectors or both of those vectors, such that you can find a vector parallel to that red dash line that connects dq and p? Can anyone think of something you can do either with rdq or with rp or with both dq, and rp to give you a vector that acts along that red line connecting q, dq, and p. Anyone? I don't like my red line because I shouldn't have used red because I already had red on the screen. But that's the line we're talking about. Anybody have anything? Anybody have any ideas? I'm going to connect this line, these points with a white line instead. Oh, white line really sucked even worse. Ooh, that's terrible. Not doing white, that's for sure. Let's do with a dark blue. How about that? Anybody have any thoughts on what vector we could use? So that's the line we're talking about there. Is that line that that line that connects the point at which DQ is located to the point P. Anyone? Okay, well, the good news is I never have anybody think of it. Well, I rarely have anyone think of exactly what the vector is that I'm wanting here. But let me give you a little bit more time to think about it. So we need a vector. So you can take DQ and multiply it by a scalar. That gives you a vector. You can take RP, or excuse me, DQ. You can take RDQ and multiply it by a scalar. You can take RP and multiply it by a scalar. Both of those give you a vector. You can add RDQ and RP. That would give you a vector. You could subtract RP from RDQ. That would give you a vector. You could subtract RDQ from RP. That would give you a vector. You couldn't do a dot product because that would give you a scalar. You could take a cross product of RDQ and RP, and that would give you a vector. So given that that's really all your options, can anybody now think of a vector that you could make that would act along that dark blue line from DQ to P? No one? Okay. So I didn't see anybody write it in the chat. So let me double check, make sure I even got the chat available now. No chats in there, so it wasn't that. All right, so you want a line parallel to that dark blue line, or a vector parallel to that dark blue line. The answer is either RP minus RDQ or RDQ minus RP. Now, if we take RP minus RDQ, then that vector would actually point from Q to P. And if I put a positive charge there, that's exactly the direction that the electric field should be acting, is from DQ to P if DQ is really positive. And if DQ turns out to be negative, guess what? It's going to be multiplied by a negative, so that would flip the vector around anyways. So it turns out that the correct vector to use is RP minus RDQ. So this one right here. So that's what it is. Now we have a vector formula. Our vector formula is going to be, say, I'm going to use blue for this. So what we have is a differential electric field element, which is going to be written as dq over 4 pi epsilon naught. Now I need the distance between dq and p, which we've already found that a vector pointing from DQ to P is actually not only the vector, but its length is the right magnitude. So I'm going to put in here RP minus RDQ vector. Magnitude of that and then square it. Okay. I don't like how unneat that is, so I'm gonna make it a little prettier. So we can do that. That'll take care of the actual R part and let you further understand exactly what R is. It's the distance between the point P and the charge dq, or at least the center of charge of the dq. So right now I have on the left-hand side a vector and on the right-hand side a scalar. If I could multiply that scalar times a vector, then I'd have a vector. So you might think, well, let's just multiply this by RP minus RDQ. But notice when you do that, then the magnitude goes up by the magnitude of RP minus RDQ. So that's a bit of a problem, because that formula is supposed to be the equivalent of DQ divided by 4 pi epsilon naught times that distance squared. I just multiplied by one of those distances, so that made that distance become like it's not squared anymore, but like it's a singular power. So to correct for that, anybody have an idea what to do? So I had that RP minus RDQ, that magnitude in the denominator, I had that squared. And then I multiplied by RP minus RDQ, which is really like a unit vector pointing the direction we want, times that magnitude RP minus RDQ. You know, that's the way you can make any vectors. You can make a unit vector and then multiply it by its magnitude. So if we do that, we've just lost one of the magnitudes in the bottom. So can you think of what we can do to recover the right magnitude and keep the direction? Still nothing, no chats, no nothing. All right. Sometimes people do get this one, but they hardly ever get the other one. So I will tell you, what we really need is something that has a magnitude of dq over 4 pi epsilon naught r squared. I had that magnitude before I wrote the vector on there, but now I have something whose magnitude is dq over 4 pi epsilon naught, just plain r. So if I wanted to make it r squared, I need to add another r down the bottom. So instead of the r squared, I'm going to make it cubed. And this is the actual formula we're shooting for. Your book attempts to do something like this, not quite as perfect, I guess. And I say perfect, I'm not trying to brag or anything. I'm just saying that this one works really well. It just might seem a little complicated, and that's probably why the author didn't do it. So this formula, you can have it on your equation sheet, and I recommend it. Okay, it's not only not numbered in the book, which is the normal rule for equations that you use on your equation sheet, but it's not even listed in there. So you're allowed to use this one. Now, while we have that in our mind, I'm going to go ahead and show you exactly how we use it. And I have a specific problem in mind. So I'm going to flip to this. Does anybody have any questions on what I said so far? Does everybody know what all those symbols mean? Okay, looks like we don't have any questions. So here's the first charge distribution I'm talking about. What I'm imagining here is an infinitely long wire. That infinitely long wire is going to be parallel to the y-axis. And in fact, the y-axis is like the symmetry axis of this wire. And it goes on essentially for infinity above and for infinity below. And I want to say it's uniformly charged. So this is a uniformly charged infinite line of charge. And I want to know, what is E at the point P? That's really the question. Okay. So that's our real problem here. I know the formula that we just derived. What I need to do is I need to use that formula. So what I'm going to do is I'm going to write right here, as soon as I change the color of this, let's say solution. So DE is equal to 4 pi epsilon naught in the bottom times RP minus RDQ cubed under DQ, and that's times RP minus RDQ, like that. So according to this, I need a DQ, I need a RP, I need a RDQ, and then I need to compute RP minus RDQ. Now, one thing I'll tell you, just like was done in your 241 class, we had a differential mass element when we were calculating the center of mass. We had it also when we were calculating the moment of inertia. Remember the integral of r squared dm, or in the case of the center of mass, the integral of x dm was the x center of mass. Well, in those dm's, we use dm was equal to either rho dv, or we use sigma dA, or we use lambda dL. Well, we're going to do the same thing here. So I'm going to give you that little caveat that dq can equal lambda dl. So that's in case you're actually dealing with something that's behaving like a one-dimensional distribution of charge. In other words, it only has a dimension, say left and right, or in this case, like up and down. Now, you could also have a surface of charge, in which case you're going to get a surface charge density sigma times dA. Or finally, you could have a volume of charge, in which case it's going to be rho times dV, where V is the volume. So sigma is the surface charge, or area density, which would be coulombs per square meter. Lambda would be like coulombs per meter, and rho would be like coulombs per cubic meter. You can also restate this as lambda is equal to dq over dl, and sigma is equal to dq over dA, and rho is equal to dq over dV. Those are all similar to the above expression. So anyways, that's what we're going to use for all of this type of stuff. So in this case, what I'm going to do is I'm going to imagine there's a little bit of charge right here. And that little bit of charge is going to be what I call dq. And I'm going to say the length of that little disk, if you will, is a length dy, because it happens to be parallel to the y-axis. And in fact, it happens to be up at a point y. Okay, so the distance between the origin and the bottom of that little point, for instance, is y. So I'm going to say dq is equal to lambda dy. So now I've got dq calculated. I'm also going to use my green vector to illustrate where r dq is. So that's r dq. And I'm going to use my green vector to illustrate where rp is. So this is rp. So now that I have that, I think we can possibly easily write out what rp is and what rdq is. So anybody want to give me what rp would be? You can use I hat, J hat, K hat notation, or you can use the less than, greater than stuff if you want, or you can tell me the magnitude and tell me which direction it points. Can someone tell me how long the vector RP is? The axis actually has a hash mark on it. Maybe that'll help.
R I hat.
Exactly. It points in the positive x direction. So we're just going to write r I hat. I'll talk a little bit later about the symmetry, so you'll know why I used r instead of x, but this turns out to be very general. It's not just in the x direction. It's really what we call in the radial direction. So that's why I used r, but that's perfect. You did RP perfectly. How about RDQ? Anybody have that one? It really is supposed to be simple. Don't nuke it is what my Navy friends say. I think you said it right. Say it again. I can't make out what you're saying. I'm sorry. It definitely points in which direction though? Does it point in the x direction, y direction, z direction, negative x, negative y, something else? Would y'all agree that it points in the positive y direction? He might have been saying J. I couldn't make it out. It sounded like two syllables. That's what. Oh, there you go. It's not RJ hat, it's YJ hat. But good job. And I think that probably was just a misspeak when you said RJ hat. So yeah, notice I made a point that it's along the y-axis. So you should just call it the distance y, and then we'll just say J hat. And remember, all vectors that have a little hat on them are understood to be unit vectors, meaning their length is 1 unit, not 1 meter, not 1 Newton, not 1 Coulomb. It's just 1 unit. So now we've got RP, we've got RDQ. The last thing I got to calculate is RP minus RDQ and the magnitude of it. So RP minus RDQ is the vector that we want. That's really easy. It's just R I hat minus Y J hat. So I've got that vector. Now all I need is the magnitude of that vector. And hopefully y'all can quickly figure that out, but let me draw it just in case. The vector RP minus RDQ is going to be a vector from here to there. So that's the vector RP minus RDQ. So hopefully that further helps you understand what exactly the magnitude will be. So anybody want to tell me what the magnitude is going to be? I'll give you a hint to start off with. Starts with a square root. Okay, it's going to be r squared plus y squared. By the way, that Pythagorean theorem even works in 3 dimensions. So if you have a vector that has an x component, a y component, and a z component, you can do x squared plus y squared plus z squared and take the square root of it as well. So this one was clearly a Pythagorean theorem. So now we have all the parts. Now all I got to do is just say, I was using black to write my solution. So I'm going to say E, the electric field, is equal to the integral of dE, the differential electric field, which I'm now going to write out with an integral. And the dq we decided was lambda times dy. And then all of that's going to be over 4 pi epsilon naught. And then I'm going to take the r squared plus y squared, and I've got to cube that. Well, I got to take the square root because that's what the length is, and then I got to cube it. So it's actually going to be raised to the 3/2 power, like that. And now I could just slip the RP minus RDQ right in here and say it's R I hat minus Y J hat, and that's it. Now, I will warn you, I've written something that definitely has to be integrated to the right of the dy, and that's not necessarily something that your math teachers would like. So I'm just going to tell you, we do that all the time in physics. I didn't like it the first time I saw it, but I have never run into a problem with doing it, so I'm going to continue to do it, and I suspect no one's ever run into a problem with doing it. So just be prepared for that in various fields. And if I just keep erasing this, it'd be really great. Okay, so anybody have any questions on how I filled all that out? All right, so now I'm going to go ahead and pull out the constants that aren't going to be problematic to me. So I'm going to say I have lambda over 4 pi epsilon naught. And then I'm going to say I have basically, because that lambda 4 pi epsilon naught freed up a little bit of stuff, I'm going to say that I have an integral of r dy I hat over r squared plus y squared to the 3/2. And then I have a minus integral of y dy j hat over r squared plus y squared to the 3/2. Now I can't really fit the closed bracket in there, but y'all know that there should be a closed bracket. So hopefully that works out. And I don't like this, so I'm going to fix this too. I really shouldn't be so pedantic and obsessive about this, but here we are. Okay, so that's really the two integrals I have to do. Let's take those one at a time. I'm going to drop the I hats and that sort of stuff, and I'm going to make some arguments about symmetry and about physics and stuff like that that'll make sense of this. But right now I'm just doing the math. Okay, so let's say one integral we have I1, or actually let's just call it I sub x because we know it's related to the x component. So I'll call it I sub x. And that's the one with the I hat, basically. So what we have is the integral of r dy over r squared plus y squared. And of course, I didn't put the range of integration, but I suspect you all realize it's going to be negative infinity to positive infinity. Now, what I want you to realize is this this particular integral has a symmetric range. It's running from negative infinity to positive infinity. And if you look at the integrand, which is r, which doesn't have any bearing on anything, but dy over the 3/2 power of r squared plus y squared. And if you substitute negative y for y, in other words, the actual process you do here, pay close attention to this, is you first replace y with parenthesis y close parenthesis. Okay, so basically in that spot where it says y squared, it's going to become plus the plus symbol that came before the y squared, plus left parenthesis y, right parenthesis, and then a squared on that right parenthesis. And then you replace the y with negative y. By doing that, you see that the negative is going to be squared as well, and a negative times a negative is a positive. So you end up getting the exact same integrand when you replace y with negative y, and that means the integrand is an even function. So the archetypal even function really is the cosine. And if you integrate an even function over a symmetric range, you can cut the range in half and just multiply it by 2. So instead of going from negative infinity to positive infinity, I can just multiply by 2 and go from 0 to positive infinity. That's what we're shooting for here. So that's one of the things that we can use to make life a little simpler. I'm going to pull the r out in front because it's really not going to have any bearing on this. And what I'm going to get is r times the integral. Actually, let me say, I want to put the 2 first. 2 times r times the integral from 0 to infinity of dy over r squared plus y squared to the 3/2. Now, to be honest with you, once I wrote that parenthetical phrase right above it, where I have lambda over 4 pi epsilon naught, curly bracket, blah, 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 I've actually completed all the physics there. So to be honest with you, you should, in principle, get, 98% or so of the credit for doing the problem if you at least got it up to this point. Okay. But we should be decent at our skill and our craft, which is, the ability to do math. And that means you should know your integrals and you should know how to do integrals. And in this case, this is a really wonderful case of trig substitution. So what I'm going to do is I'm going to say, let y equal r tangent theta, then dy is equal to r secant squared theta d theta. And not only that, tangent theta is equal to y over r. So you can make a little triangle and see your theta there, see your y there, see your r there, and then see your square root of r squared plus y squared up here. I'm going to undo that because it's way too small. But basically, you have that little triangle there. And that little triangle allows us to make some sense of the range of integration. So this is the angle theta, there's y, there's r. This is the square root r squared plus y squared, like that. So if I go to y equals infinity, what I'm really doing is letting theta go to pi over 2, basically 90 degrees. So now that I do that, I can plug this stuff in. I'm going to have 2r integral theta equals 0 to pi over 2 of dy is going to be r secant squared theta d theta. And then in the bottom, I'll go ahead and do something kind of smart. I'm going to factor out an r squared because you can see by making y r tangent theta, I'm going to have an r squared in both terms. So I'll say a r squared times 1 plus tangent squared theta, all that to the 3/2 power. Anybody have any questions with that so far? Now we're going to use a trig identity. 1 plus tangent squared is actually equal to secant squared theta. And I want you to realize that r squared to the 3/2 actually becomes r cubed. And I have a r up at the top with the 2r out in front. That's 2r squared. So my result is currently 2r squared.
Shouldn't there be a plus between R2 and 1 plus 10 tangent square of theta?
A plus between where now?
R square and the parentheses.
No. So what happened was I replaced y with r tangent theta. So it'd be r squared plus r squared tangent squared theta. And I went ahead and factored out the r squared from it, from both of the terms. Are you seeing what I'm talking about now?
Yes.
Okay. So yeah, that's what basically happened. So hopefully that makes some sense. Now, just like r squared to the 3/2 power became r cubed, secant squared to the 3/2 power becomes secant cubed. So now what I have is secant squared under secant cubed, which would be d theta over secant theta. But secant theta is 1 over cosine theta. So this all of a sudden just becomes cosine theta d theta. Everybody follow what happened there? All right, so I now have 2 over r. Anybody have any questions on that? I have 2 over r, integral cosine theta. We know the derivative of sine is cosine, so the integral of cosine is sine. So really, I'm going to do the sine of pi over 2, which is 1, minus the sine of 0, which is 0. So really, the whole answer is just going to be 2 over r. So I've now completely figured out this integral. And the answer is, as I said, 2 over r. Let me put some qualifiers in here just so you might realize later what happened. So the so the integral of cosine theta d theta became the sine of theta, and we evaluated that from 0 to pi over 2. And of course, that's just equal to 1 minus 0. And then that was all times 2 over r, which we had already clarified by crossing out this with all but one of those. And that just gave me 2 over r. Okay. So that's the integral for the x. The integral for the y is actually not that bad, and I'm going to attempt to fit it in here because I'm pretty confident I can make it and without it being obscured. So I'm going to say integral iy, and I'm going to drop the j hat, and I'll keep the negative. But what we're going to have here is the negative integral of y dy over r squared plus y squared to the 3/2 power. Okay. Now, in this case, I want you to realize if I replace y with parentheses, y close parentheses, and then replace y with negative y, I will get, in fact, the negative of the integrand. So this is, in fact, an odd integrand. And because of that, and because of the fact that it's integrated over a symmetric range, that it actually is going to give you 0. So we know from that alone that the integral will be 0. Let me write that in a different color. Now, you don't have to necessarily take my word for it, but it is that. But in this case, all we have to do is do a u substitution. I'm going to let u, so let u equal r squared plus y squared. So du is equal to 2y dy. So I need a 2 in there. And if I put a 2 in there, I should also put a 1/2 in there. So what I'm going to do now is I'm going to say negative 1/2 integral du over u to the 3/2. And that gives me negative 1/2. And the integral of u to the negative 3/2 is u to the negative 1/2 divided by negative 1/2. So you see that part cancels out. And now I'm going to get 1 over square root r squared plus y squared, because that's u to the negative 1/2. And I'm going to evaluate that from negative infinity to positive infinity, which you can see they're going to give you the same answer in both cases because the y squared integrated or taking the limit as y approaches in negative infinity still gives you 0. And then when you take the limit of r squared plus y squared square root in the denominator as y approaches positive infinity, you get the exact same thing again. So the result is actually 0. So we could have done it just by recognizing the integrand was odd. We could have done it by the actual calculation. And now I'm going to talk about the physics of this. If you look at the diagram that I have up top where I show RDQ and RP, you can see that the actual DE vector as a result of that points this way. Oops. It's supposed to be actually parallel, so I didn't do as good a job as I would have liked to. But anyways, let's see if I can do a little better. So that's my little differential E vector right there. And if you consider another differential charge element, say right here at a distance y down, you can see that the y component of that one is going to be exactly the opposite of the y component of the one we just did. And since you can do that for every differential charge element on the positive side of the x-axis or the y-axis, you can see that it's always going to cancel out. So just from a physics standpoint, we should expect the y component to cancel out. So now that's a third way that we've learned. Now all I have to do is take my integral I sub x, which is 2 over r, and combine that with the I hat and with the lambda over 4 pi epsilon naught. So I'm now going to say that E, well, actually, I should stick to black, I guess. Whoa, no, I did not mean to do that. I should stick to black, I guess. Okay, I'm just going to randomly put pencil marks everywhere. Okay, so E, which we said was the integral of dE, has now become lambda over 4 pi epsilon naught times 2 over r. Notice that's 2 over r. Notice the lambda over 4 pi epsilon naught was already there, and all I need now is the I hat vector. So what we find is that the electric field at the point P that we talked about is actually equal to lambda over 2 pi epsilon naught r, pointing in the I hat direction. And now I want to explain a little bit about that. Yes, it is pointing in the I hat direction, but if you look at this wire, okay, that was terrible. I'm trying to fix this, make it a little better. If you look at this wire, what you realize is it has cylindrical symmetry, meaning I can rotate it. That's a putrid looking eye. Anyways, meaning I can rotate it about the axis right through the center by any angle that I want, an itty bitty angle, a big angle, all that doesn't really matter. I can rotate it and it'll still look the same. And what that tells us is that it has some kind of symmetry. So this I hat should point radially away from the y-axis at all points in space. So it might be even more correct to say that the electric field is actually equal to lambda over 2 pi epsilon naught r. Well, I'll use the big R again, r hat, where r hat is just a vector that points radially outward. For instance, if you looked at your coordinate system like this, that's your y-axis. This will be your x-axis, and then this right here would be your z-axis. So if I took a point right here, r hat would point this way. If I took a point right here, r hat would point this way. If I took a point back here, r hat would point that way. So you can see the symmetry of it just makes it so that in reality, all we're talking about is the electric field is always going to point away from the charge distribution, which is an infinitely long line segment. And it is uniformly distributed. Of course, if that was negative, then it ended up being multiplied by a negative number. The lambda would come out negative and the R would actually point inwards. So both of those are correct, but really the black one is the one that's sort of more correct because it's more general and covers the whole thing. Does anyone have any questions on that? All right, now I'm going to tell you the same thing I told my face-to-face students yesterday. That might have been a really scary problem. be honest with you, it is the second most complicated problem you will encounter this entire semester. There's one more that's going to be even uglier, and that's basically using an ugly, a potentially difficult formula, if you will. In this case, the potentially difficult formula was Coulomb's law for integrals. And later on, we'll be doing something called Biot-Savart law, which is just as actually is way more complicated or potentially complicated than this one, because it's literally the same thing, but it has a cross product in the integrand. So it's really, really a big deal. That one will be the hardest. But again, I will show you a nice way to break it down and do this kind of stuff. So what I recommend you doing is go into your book. Your book solves the same problem, and he makes really ingenious physical arguments of what the electric field is going to be. And he starts with these little blue vectors that I put on the end of the position P. He starts with those and uses the symmetry of the physics and makes beautiful arguments that makes his math really, really easy. I like doing it this way because I suspect most people in physics are not that physically understanding yet, so they don't have quite as much maturity to make really physical arguments so well. I tried to show you all the physical arguments, but I just showed you brute force how the math worked out, and we got it. So what's going to happen is you can read his technique, you can read my technique, you can watch my video over again, and you can watch. I've actually solved this probably 3 or 4 times on my YouTube channel, so you can find a ton of examples of me doing it. And so you can watch it over and over again, as well as watching this video. And I think between the two of those, his technique will help you understand my technique, and my technique will help you understand his technique. And then you should be able to more or less regurgitate it. Okay. But that regurgitation should be somewhat, if not mostly, from understanding, not just from memorization. So give that a try. I'm going to do a couple other examples as well, but that's basically the answer. It's also kind of interesting, if we had a spherical charge distribution, like a point charge, we know that the electric field, I just derived that for you, or I just gave it to you. The electric field for a spherical distribution is just Q over 4 pi epsilon naught R squared, right? So, for instance, if you imagine a light bulb at the top, at the center of a room on your ceiling, if you go, say, 1 meter or 1 foot from that light bulb, it's going to be a little less bright than right on the light bulb, but it'll still be pretty bright at 1 foot away. If you then go 2 feet away from that light bulb, the brightness of that light is going to fall not to 1/2, but to 1/4, because the brightness of the light goes like 1 over R squared, because it's a point of light when you start comparing the dimension you are away from the light to the size of the light. So this E equals Q over 4 pi epsilon naught R squared says that a light bulb should have the light fall off as 1 over R squared. But this case where I had an infinitely long bit of charge, that fell off like 1 over R. So if you replace that light bulb with a long bar of light and you go 1 foot down, it'll be pretty bright, but not quite as bright as being right on the bulb. But if you go from 1 foot away to 2 foot away, it's only going to be half as bright instead of 1/4 as bright. So that's why you see a lot of long fluorescent light tubes, because the light is actually a little less drastic in its fall off as you move away. We'll also determine that when you calculate the electric field for an infinite plane, that'll turn out to have 0 dependence on R, at least as long as you're close to the plate. So when you're close to the plate, it has no dependence whatsoever. So that's also why you'll see sometimes when you go to a classroom, or I think the last time I saw one was at a Great Cuts, they have lights, those long fluorescent tubes, but then they have a dispersive plate on the top of it that disperses the light and makes it look like a light sheet as opposed to a light rod or a light bulb. That's their attempt to take the R dependence out of it, and it does make the light sort of fill the room a little better. So anyways, hopefully that stuff can help you better understand why it went from 1 over R squared to 1 over R to no R dependence. So let's start another one. Anybody have any questions on anything before I start another one? Okay, so with this one, what I'm going to do is I'm going to imagine a ring of charge. Okay, and that was supposed to make my horrible drawing better. There it is. Okay, so now I've got a ring of charge. I'm going to attempt to center that up on a XYZ coordinate system, like so. And now this axis is going to be the x-axis, this axis is going to be the y-axis, this axis is going to be the z-axis. And I'm going to say this distance right here from the center of the ring of charge to, which is the origin, to the point P that we wish to know the electric field at, has a distance z. Okay. I'm also going to say that the ring of charge has a radius of big R. Okay. And I'm going to say it's uniformly distributed charge over the ring. So a ring has a radius R and a total charge Q equals lambda times 2 pi R distributed uniformly along itself. E at P is the question. Okay, so that's what we want to know. We want to find the electric field at P. I'm going to again use my formula. I think I'll work it out in red this time. So solution, I'm going to use E is equal to the integral of dE. And I'm going to use the fact that dE is equal to dQ over 4 pi epsilon naught RP minus RdQ cubed times RP minus RdQ vector. Okay. So again, I've got to figure out what dq is and stuff like that. So let's get started on doing that. What I'm going to do first is I'm going to imagine going out an angle theta. So this angle right here is theta. And then I'm going to imagine allowing that to vary just a little bit so that I now have an angle right here that will be d theta. Okay. That means that this little line segment right here, which is what I'm considering to be dq, is a charge per unit length. So that would be a lambda times the length of that little arc. Using S equals R times theta, can someone tell me what that length of that little arc is? So remember, S equals R theta, that's the definition that we use, or that's what we use to figure out the definition of radians. So can anybody tell me what that little length, you might call it ds, for instance, is? Nothing? Okay. Well, if that little bit of arc is ds, then ds is actually equal to r d theta. So I'm going to write it like that. So now we've figured out DQ. I need a vector that points to RP. So let me pull out my green pencil. This vector right here, that vector is RP. And this vector right here is RDQ. Now, it might help you. Actually, I should probably make that a little clearer. So I'm saying this vector is basically, it's basically that red line that I put there, but I didn't want to cover up the red line, so I tried not to. But it's basically that little vector. And you can also look and see that it obviously has X component. And of course, it also has a Y component. And that's the part that we really need. So anybody want to take a poke at what RP is? That should be the easy one.
Z,
Yes. And which direction does it point?
K hat,
Exactly. So K times Z times K hat. And how about RDQ? This one's a little more complicated. Anybody think they know what the X component is? How about I'll give you the X component and see if y'all can figure out what the Y component would be. Okay, that's the X component. What do you think the Y component is? It's the length parallel to the y-axis, which is going to be r times the sine of theta. So that's that. And of course, it's not that, well, it might be confusing when you go to look at the magnitude of RP minus RDQ, because that's going to be the magnitude of Z K hat minus R cosine theta I hat minus R sine theta J hat. So that might not be that easy for you to understand. But if you work out the math, you will find that it's actually the square root of Z squared plus R squared. Okay. You can sort of see that if you actually draw the vector on here, because you'll notice, oh, the green vector in the XY plane just has a magnitude of big R, and the green vector on the Z axis has a magnitude of Z. They're clearly perpendicular to each other. So Pythagorean theorem would tell you that it's going to be that. So now I can go ahead and say that the electric field E is equal to the integral of dE, which equals the integral of, I have dq, that's going to be lambda r d theta. So lambda r d theta. And then I have rp minus rdq, which is going to be z k hat minus r cosine theta I hat minus r sine theta j hat. That's all going to be the vector. And all that is going to be divided by 4 pi epsilon naught times. Now I'm going to write r squared plus z squared to the 3/2 power. Now I think if you think about this, for the angle theta, you're going to have a little vector that points, it has a component parallel to the z-axis for the dE, and it has a component that's parallel to the x-axis and another component that's parallel to the y-axis. But I think if you look at theta plus 180, you're going to see that the X and Y components of that electric field is exactly going to cancel out the X and Y components of the original one at theta. So I think you can realize that integrating cosine theta I hat and sine theta j hat are both going to give you 0. Another way of looking at it is, notice this integral is everything's about theta. So cosine theta, if you integrate cosine theta d theta from 0 to 2 pi, you're going to get 0 because there's just as much area above the x-axis as there is below the x-axis. And if you integrate sine theta from 0 to 2 pi, you're going to get just as much above the axis, namely the first half, as you do below the axis, the second half. So that's going to give you 0 as well. So this integrates to 0 and this integrates to 0. You can get that, as I said initially, by considering theta and theta plus 180. So that's the physics way, but you can also get it from the mathematical way that I just showed you there. So we're really only left with the other term, which gives me integral lambda r over 4 pi epsilon naught. And then you're going to have an integral of z d theta k hat over r squared plus z squared, which, by the way, are completely constant. Okay. So, and this is going to go from theta equals 0 to 2 pi. So I'm going to get lambda, let's say lambda z r k hat over 4 pi epsilon naught, over 4 pi epsilon naught times r squared plus z squared to the 3 halves times the integral d theta from 0 to 2 pi. Okay. So that's going to be, and notice how I group things. That's going to be z times lambda times 2 pi r over 4 pi epsilon naught r squared plus z squared to the 3 halves times k hat. And the reason I grouped it that way, you can see that lambda times 2 pi r is exactly the total charge Q from the top. So we can write it either way. We can say E is equal to this, or we can say E is equal to Q Z over 4 pi epsilon naught r squared, plus z squared to the 3 halves in the bottom, and it points in the positive k hat direction. Any questions on that? All right, now I'm going to show you an entirely different way because we only got a couple minutes left. We got 8 minutes. I'm going to use this as a DE. In other words, I'm going to say DE is equal to Z times DQ over 4 pi epsilon naught parenthesis r squared plus z squared to the 3 halves power, because the next problem I want to solve is going to be, instead of a ring of charge, it's actually going to be a disk of charge. So let's again imagine drawing a circular disk. Okay, there's my circular disk. That was really horrible. It's all crooked and stuff. That was, well, that's crooked too. I hate that. I hate this. There you go. That's a little better. Okay, so now I'm going to draw my axes again, but now this is not a ring of charge. This is a disk of charge. And this is a z-axis, this is an x-axis, this is a y-axis, And I'm going to say this thing has a radius that is big R, okay? But now I'm going to imagine that inside of it, let's use a blue, I'm going to have another ring of charge, if you will, like this. Oops. Okay, that's a ring of charge of radius little r, say. Okay. So that's a ring of charge of radius little r. And you can imagine if you actually cut that ring of charge right along the x-axis and then laid it out flat, it would look like this. In other words, where you cut it, it would leave this little triangle on each end, and this inside part would have a distance or a length of 2 pi times r, and this outside part would have a length of 2 pi times r plus dr. And the reason why is because this little distance right here is dr. So what we're going to do is we're going to say that this is my dq, which is equal to a charge per unit area, sigma, times 2 pi r dr. So you can see we're actually treating it like it's a rectangle. We're ignoring that little triangle on each end. I can actually show you that this is actually technically the whole area of that ring is pi parentheses r plus dr close parentheses squared minus pi r squared. And if you calculate that out and square the binomial, that sort of thing, what you'll find out is this differs from that differential area element, 2 pi r dr. That only differs by a dr squared. And if dr is supposed to be done by taking the limit as dr goes to 0, then dr being like 0.000001 means the dr squared is going to be like a 0 followed by a decimal followed by like 12 zeros and then a 1. So yeah, you can ignore dr squared compared to dr. So that's why that actually works. I'm going to say we're trying to calculate again the electric field at let's say the point 0, 0, z. Okay, that's what our question is. It's uniformly distributed. So my solution is going to be, I'm going to use E is equal to the integral of dE, but this time dE is going to be dQ times Z over 4 pi epsilon naught. In this case, it's actually the R that's changing. So I'm going to have to, I'll put Z squared plus little r squared to the 3 halves. Okay. And we obviously know it's going to be pointing in the k hat direction from the same symmetry arguments we made before. So if I go to do this integral, I can say E is equal to Z over 4 pi epsilon naught integral of sigma times 2 pi r dr k hat over z squared plus r squared to the 3 halves. I'm going to say let u equals z squared plus r squared, then du is equal to 2r dr, which we already have a 2 up top. So what I'm going to do is I'm going to cancel out this pi with this pi. I'm going to leave that 2. I'm going to say this this guy, and this guy all make up du. Okay. So now what I have is Z sigma K hat over 4 epsilon naught is equal to the integral of u to the negative 3 halves times du. This is going to be equal to, of course, sigma z k hat over 4 epsilon naught times, in this case, it's going to be 1 over negative 1/2 times, in this case, I will put a curly bracket, and it's going to be 1 over the square root of z squared plus r squared. And I'm going to evaluate that from r equals 0 to big R. Okay. So this is going to give me sigma z over 4 epsilon naught k hat. I know I'm just about out of time. Oh, crap. It's just running out of time. Let me finish this up. This is going to become a -2 out in front. Y'all can, if you need to split, it's okay. I'm going to finish this up because I have to. But anyways, this was a sigma. So I'm now going to get a -2 out in front from that -1/2. And that, of course, can help me cancel out that 4 down the bottom to make just a 2 in the bottom, which oddly enough is exactly what I want. And when I evaluate this at r, I get 1 over the square root of z squared plus r squared. And when I evaluate this at 0, I get 1 minus 1 over, or excuse me, I get 1 over the absolute value of z because it's the principal square root of z squared. Okay. Now I can go ahead and distribute that negative and that z, and I get something that's very nice. I get sigma over 2 epsilon naught. I'll leave the k for the end. When I multiply through by z, and since I did the negative, I'm going to reverse the order. This is just going to be 1 minus 1 over the square root of z squared plus r squared, like that. And the z is really the variable. And all that is multiplied by k hat. And that's the electric field. That's it in a nutshell. It turns out if you let r be much greater than z, then E goes to sigma over 2 epsilon naught k hat, which is what I was telling you earlier. For an infinitely large plate, the electric field is sigma over 2 epsilon naught. Notice it has no r dependence whatsoever, no z dependence in this case, because z is the distance away. But that's it. We're done. Anybody have any questions on that? I'm going to wait for the last person to leave. Other than that, you guys are free to go, and y'all have a great weekend. Make sure you knock out the September 25th, which is Monday. That's your online test, your second online test. So make sure y'all don't forget to do that. And have a great weekend. Stay safe and holler for anything.
Thank you. We continue with chapter 21 next week, right?
Yeah, we're almost finished with 21. There's a little bit of stuff that I got to do with it, but I'm jumping right into 22 next time as well.
All right, sounds good. Thank you. Have a good weekend.
You too, Tony. See you. See you, Tao. Randall saying, you know, have anything? Don't worry if you look scary with this math. That's pretty normal. It's going to happen like this over and over in your career. So, yay! I like it. It gives us a little bit of excitement. Anybody need anything? Randall, are you still there? Saying? Oh, he's still writing down. Saying this. Gotcha. I'm going to be posting this to Google Docs in about 2 minutes, so you have that as well. And then, of course, you can always watch the video, or you can watch the 50 versions of the video that I've done in the past. But that's it.
Excuse me, Professor, is the chapter 21 homework still due Tuesday or Monday?
No, I should. Matter of fact, I think I've already changed that. I'm going to go ahead and make that due the following week. But that's going to make it where you're probably going to run into a little bit of 22 because we will finish 22 next week. So just be prepared to do 21 and 22 next week.
Okay, thank you.
I'll stagger them as much